After starting an engine using the aircraft battery, the generator or alternator is used to recharge it. The fact that the battery is being recharged is indicated on the system ammeter as a high load. Initially this will be quite high, but should quickly reduce as the battery is recharged. A word of caution here. If the load increases or remains high, then this could be an indication of a faulty battery. Remember, a high charge rate could result in a battery overheating and suffering damage. Voltmeters have a high internal resistance. They are connected in parallel with the circuit to measure the voltage between 2 points. Ammeters have a low internal resistance and are placed in series with the circuit to measure the current through the load. Two types are used in light aircraft. The first has the zero position on the dial over to the left. It indicates the actual load on the alternator. Because of this, it's commonly called a load meter. The other type has the zero position in the center of the dial, and its needle indicates the current flow into and out of the battery. Abnormal conditions may arise in an electrical circuit for a variety of reasons. For instance, a breakdown of the insulation on one of the cables carrying the supply to a component will cause a dramatic rise in the current flowing in that cable if it comes into contact with the metal of the airframe. There are several serious problems inherent in this situation. Firstly, and probably least serious, is the fact that the component being fed by this particular cable will cease to operate. Secondly, if the circuit was not protected, the current which would flow through this short circuit, for that's what this malfunction is called, would be so great that it could cause the power generation circuit, the alternator or generator and the battery, to fail. This would leave the aircraft without electrical power. Thirdly, and potentially the most serious, there is the risk of fire. At the point where the unprotected cable contacts the airframe metal, there will undoubtedly be sparks, which will ignite anything in the vicinity, and the cable itself will get so hot that more insulation will be melted from the cable, making the situation worse. Although there are a number of protection devices used in aircraft electrical systems, we'll look at only two of them. These are fuses and circuit breakers. The fundamental difference between fuses and circuit breakers is the time it takes for each of them to operate from the moment of maximum fault current flowing in the circuit. A fuse normally breaks a circuit before full fault current is reached, whereas a circuit breaker operates to break the circuit after full fault current is reached. The circuit breaker can also function in certain circumstances as a switch, opening and closing a circuit as required. The most common type of fuse in use on light aircraft is the cartridge fuse. It consists of a tubular glass or ceramic body with the fuse element running through the center, connected to two brass end caps. The fuse operates, or blows, when the current flowing through is sufficient to melt the fuse element. The time this takes varies inversely with the current. All fuses are rated at a specific current value, that current being the current the element will carry continuously without unduly heating up or deteriorating. The rating of a fuse in a particular circuit is such that it is not less than the normal current flowing in that circuit, but will blow at a current level below the safety limit of the equipment or cable used. For this reason, only the specified fuse rating should be used in a particular circuit. A fuse that has blown may be replaced with another of the correct rating, but only once. If the replacement fuse blows when the circuit is reactivated, then there is obviously a defect in the system, and the fuse must not be changed again until the circuit has been investigated. Fuses which have a greater rating than that specified for a particular circuit must never be used. The consequences will most probably include greater damage being caused and may be an electrical fire. Circuit breakers are fitted, as are fuses, to protect equipment from overload or fault conditions. They incorporate a heat-sensitive tripping device and a manually operated trip reset switch. The type of circuit breaker shown in the diagram can be rated from between 5 to 45 amperes. The push-pull button is shown in the operated position. The white marker band is specifically there to draw attention to the fact that the circuit breaker has blown. A circuit breaker which has operated, or popped, may be reset just once. Do not be tempted to reset it a second time. If it's popped twice, then you may be sure that an electrical fault is present, and resetting the circuit breaker twice will only exacerbate it. This diagram shows a simplified alternator control circuit. For the purpose of this lesson, we'll assume that our aircraft is fitted with an alternator. From the point of view of the pilot, generator and alternator control circuits are very similar. The only difference worth noting is the rectifier shown here. This changes the alternating current output of the alternator to direct current, a procedure which is unnecessary with the generator because its output is direct current. At the top of the diagram you can see the buzz bar, which we previously said was a distribution point for the output of the alternator or generator. To the left is the field circuit, and to the right is the power circuit. The field circuit carries a relatively small current. The current flows through the field windings and is used to generate a magnetic field inside which the armature of the alternator rotates. The field circuit of this alternator is protected by a 5-amp circuit breaker. Just below that on the diagram is the alternator master switch, which you can see in the photograph is on the left of the row of switches. Immediately adjacent to the alternator master switch is the battery master switch. These two switches are usually mechanically interlocked so that the alternator cannot be operated without the battery. If either the field circuit breaker or the alternator master switch is opened, then the alternator field becomes inoperative and the alternator will not produce any output. Also in the field circuit is the over-volts relay. A relay is just an electrically operated switch. This relay will operate to open the field circuit if the alternator output voltage rises above 16.5 volts. The effect will be the same as if the field circuit breaker or alternator master switch had been opened. The alternator will not produce any output. In this particular aircraft type, the overvoltage relay can be reset by switching off the alternator master switch for about 2 seconds and then switching it back on again. Adjacent to the alternator is the voltage regulator. As its name implies, it controls the voltage output of the alternator, in this case between 14.5 to 16 volts. The power circuit passes the whole of the output of the alternator to the busbar, where it's then distributed to the individual components in the aircraft. The rectifier is necessary, as we said earlier, to convert the alternating current output of the alternator to direct current. The load meter measures the total current flowing from the alternator to the busbar. This illustration shows a simplified electrical wiring diagram of a typical light aircraft. Notice that in this aircraft all of the loads but 2 are protected by circuit breakers of varying amperage. The exceptions are the power side of the starting circuit and the battery. Although the power side of the starter motor circuit is not protected, the control part of that circuit is. Note that the starter switch gets its supply from the bus bar via a 15-amp circuit breaker. A starter motor will take considerably more than 15 amps when it's first selected upon engine start. In fact, the initial load on the battery will exceed this figure by more than a factor of 4. That sort of current flow would cause the circuit breaker to pop open in an instant, and if it was flowing through the starter switch, it would either melt its contacts or weld them together, neither prospect being particularly appealing. To prevent either of these occurrences, the starting current is taken from the battery and passed through a starter relay. The starter relay is remotely controlled by the starter switch. When the starter switch is selected, it sends a supply to energize the coil of the starter relay. The starter relay has large contacts which are capable of easily passing the very high current required by the starter motor, so the starter motor rotates the engine. Try pressing the starter switch now and note how the supply is passed through the starter relay.